Exercise 3E looks at when either velocity or acceleration functions are given in terms of displacement. So this is when you're really reading very carefully, or you're really paying attention to the details of a function. So what you don't see the presence of is the time variable. So the only rules we have to connect displacement, velocity and acceleration involve time. So when we've got this situation, say velocity in terms of displacement, we somehow have to get time into the situation. So I'll come back and I'll read all of the all that's written there, but if you just have a look over here on the side, we know that if velocity was a function in displacement, we know that velocity, we could be given that, velocity as a function of displacement. Then we start to have a think, well, what do we know about velocity and what do we want to get introduced? We want to get time introduced. And the only thing we know about velocity in terms of time is that velocity is dx dt. Now, it doesn't make too much sense to say that dx dt is equal to a function in x. And so, because we can see there's no t here, but there's one really simple way to fix that, and it's turn each side upside down. So talk about dt dx, so the variable that you're differentiating with respect to is x, becomes this expression. Whatever this expression is, at least it's got an x in it, and it makes sense to say that something called t was differentiated with respect to x, and we ended up with this. Now, from there, keep in mind we want t. How would we get t? Well, to get t, we would go backwards. And going backwards in this situation is to integrate. So we know that t can be found by integrating 1 on f of x with respect to x. Now what does that give me? It gives me an expression about t. And we actually know that this is going to have something with x's in it. Some more x's. And it'll have a constant, and it doesn't really matter what the constant is. But what we have achieved, and remember, this is like an expression in terms of x. Now, if we work with that and make x the subject, and so we've got our t, we might have minus c, we might have a whole lot of other things going on in order for us to take this function in x and reduce it to a single x to make x the subject. So lots of things are going on here. It doesn't really matter because what we've achieved is x in terms of t. And it won't be this simple. We might have had to square the t, we might have had to divide by some numbers, but that will come out. The most important thing is you can see that through this process, we've created an expression for displacement in terms of time. And then we go back to what we know. To get velocity, we differentiate this. To get acceleration, we differentiate again. So, thinking about the steps, they're more little techniques. There's nothing overly special. This just required a substitution. It was then this tricky technique of turning each side of that equation upside down. And then the understanding that we can go back to t by integrating this function. and then thinking about making x the subject. So that's basically what it says here. When velocity is given as a function in x, integration and differentiation with respect to time can't be carried out. No, that makes sense. To overcome this, a function for displacement in terms of time will need to be produced. Well, that's what we've done here. An expression for displacement in terms of time. And to use this, we use the reciprocal. Well, I suppose from there to there was the reciprocal. And then we take the integral of both sides. Okay, like it says, let's do this example. You're given v is equal to negative 6x cubed. There's our hopefully really obvious piece of information that says this is not straightforward. That's not a t. Given that, find an expression for t in terms of x and then x in terms of t. So we've got that v is equal to minus 6x cubed. We can substitute for v. We know we need to, the thing that's missing is t. We need to get t into this. So if we call velocity dx dt for now is equal to that. It doesn't make any sense at the moment. However, if we turn it upside down or take the reciprocal of both sides, then we can see that if t was differentiated with respect, we got this result in terms of x, which is fine. T was differentiated with respect to x, the variable was x. So the next step after that is to say, well, I want to know what t was, so we need to integrate. Integrating, take out your constant, add 1 to your index, divide by your new index, and you get an expression for t with a constant. Now, the reason you're given this information is so you can evaluate the constant. It says when t is 0, x is 1. Subbing that in, you get that c is minus a 12th and t is equal to this. We still need an expression for x in terms of t. So I guess we've done the first bit. We've got t in terms of x, but what will be much more useful is x in terms of t. And why would that be the case? Because then we could differentiate our x, which is displacement, and we could come up with a velocity or in terms of time, and then acceleration in terms of time. So all the process involves now is just rearranging an equation. So we had this equation here, chose to multiply everything by 12 in this line, then took the 1 across and it became plus. Then it's the same as cross multiplying, I guess, and then getting the x squared by itself, or just swapping the positions of those two. So x squared is 1 over that, and then taking the square root of both sides. Now that we've got an expression for displacement in terms of time, we can go back to our previous processes of differentiating to get velocity in terms of time and acceleration in terms of time. If you want to try this next example, then you could pause the video now, and because I'll just continue on and write up the solution. If you would like to see how you went, then by all means, like I said, pause now. Okay, we're told that v is equal to 1 plus x. So clearly velocity is in terms of displacement, and there are our alarm bells that this is a different situation. We know that the initial displacement is 1 metre. What does that mean to us? Well, initial is when time is 0, x is equal to 1. Probably can remember from the previous example, we're going to need that when we do our integrating in order to find the constant. So we're setting about finding t in terms of x. So we know that we've got to get t into it. All that we have at this stage is that velocity could potentially be called dx dt. So we're just going to replace the velocity with dx dt and keep the 1 plus x. It doesn't make sense to say something was differentiated with respect to t and we've got x's in it. So this process that we do here is we take the reciprocal of both sides, turn them upside down. So now we're saying an expression about t, which had x's in it, ended up being 1 over 1 plus x. And that makes sense. We want t, so we know that we would have to take the integral of 1 over 1 plus x with respect to x. Now, really, any time that you're integrating and your variable is in the denominator, you know that there needs to be careful consideration. In this case, there is no point calling this 1 plus x, bringing it all up to the minus 1, because we'll be adding 1 to the index, which will give us a 0 and trying to divide by 0, which then hopefully takes us to, well, this is a situation where this came from a log. So to get to t, we had the log of 1 plus x. And if you're unsure, do a little differentiation of this over on the side. Differentiating with respect to x, the log of 1 plus x is simply 1 over 1 plus x, differentiating anything to do with the x, which is just a 1, so it's just 1 plus x. We know that we would have a constant. We then know we must work out the value of the constant. We had that initially the displacement was 1, so we've got the log of 2 plus the constant. That gives the constant the value minus the log of 2. So we have an expression for t in terms of x, and we must get x on its own. So it's going to be take a little bit of understanding of exponentials and logs, which is part 2. It says get x in terms of t. We know that by definition, if you take the log of a number, you get the power to which this base had to be raised in order to give that number. So that number, 1 plus x, was e to this power, t plus log of 2, and that gives me that x is e to the t plus log 2 minus 1. And then this second example is almost identical. The process is almost identical. It's actually a little bit easier because the displacement expression gets turned upside down, becomes really nice. Taking the integral with respect to x is not difficult. Finding the constant is really easy. Finding, well, I didn't even really actually get x by itself because it was simply to find the displacement after 4 seconds. So you can sub t is equal to 4 into this expression here and round your answer to 2 dp and you'll get 0.93 metres. You should be right now to do that. Other questions from that exam exercise?